Hello all. In this video, I am going to give an overview on iPhone forensics. The main goal of iPhone forensics is extracting data and artifacts from iPhone without altering any information on the device. iPhone forensics can be performed on the backups made by iTunes or directly on the live device. Forensics performed on iTunes backups are called escrow key attacks. In this video, I am going to focus on live device forensics. To perform live device forensics, I am going to use open source Toolkit released by researchers at Sogeti Labs. In order to do forensics, first we have to create our forensic toolkit and load it on device. Suppose if you have a computer which is protected with OS level password, we can still access the hard disk by booting a live CD or by removing the hard disk and connecting it to other machine. When we compare computers to the iPhone, it is an embedded device, so it is not easy to take out the chips and dump data in it. To perform iPhone forensics, we use live CD approach. As iPhone has only one serial port, we are going to load custom OS over USB to access hard disk of the device. But the problem here is iPhone only loads firmware which is signed by Apple. To load our custom OS, we need to understand iPhone functions at operating system level. iOS, previously known as iPhone OS, is the operating system that runs on iPhone. iOS is basically a zip file ships with .ipsw extension which contains bootloader, kernel and some built-in applications. Let's look at iPhone boot up process. When we turn on iPhone, it walks through a chain of trust which is a series of RSA signature checks among different OS components in a specific order. The chain of trust begins with boot ROM. Boot ROM is read-only memory and it is the first stage of booting an iOS device. Boot ROM contains all the certificates to signature check the next stage. iPhone basically operates in three modes: normal mode, recovery mode, DFE mode. When we switch on iPhone, it gets started in a normal mode. In normal mode, boot ROM starts off some initialization stuff and loads the low-level bootloader by verifying its signature. Low-level bootloader signature checks and loads the stage 2 bootloader, which is iBoot. iBoot signature checks the kernel and device tree, and kernel signature checks all other user applications. Whereas in DFE mode, boot ROM signature checks the second level bootloaders, and bootloader signature checks the kernel, and kernel signature checks the RAM disk. RAM disk is part of OS which gets loaded into RAM during an iOS update. Later, this RAM disk loads all other OS components. In forensics, we will create a custom RAM disk with all our forensic toolkit and load it on iPhone volatile memory. As signature checks implemented at various stages in the boot sequence does not allow to load our custom RAM disk, so we have to bypass all the signature checks. In the chain of trust boot sequence, if we compromise one link, we can fully control all the links that follow it. Hacker community have found several vulnerabilities in boot ROM, using which we can flash our own bootloader and patch all other signature checks in all the subsequent stages. Apart from signature checks, every stage is also encrypted. These encryption keys can be grabbed from jailbreaking tools. Boot ROM vulnerabilities can only be fixed in hardware, so all the existing boot ROM vulnerabilities cannot be fixed. Hackers found boot ROM vulnerabilities in A4 chips and they are trying to find similar sort of vulnerabilities in A5 chips which are used in iPhone 4S. To perform iPhone forensics, I am going to use iPhone 4 GSM model with iOS 5. There are mainly 5 steps involved in performing iPhone forensics. First, we have to create and load our forensic toolkit onto the device without damaging any evidence. Next, we have to establish a communication between the device and the computer. Once we establish a communication, we have to bypass passcode restrictions on the device so that we get access to file system of the device. But the file system is encrypted, so we have to find a way to decrypt the files and view it. And the final stage in iPhone forensics is recovering the deleted files. To create and load our forensic toolkit, we are going to use the tools which are released by researchers at Sogeti Labs. These tools basically contain few Python scripts, binaries and few shell scripts. The goal here is to build our own custom RAM disk with all our forensic tools and patch the RAM disk signature check in kernel. Later, we use jailbreak tools to load our kernel by patching boot RAM signature checks. I have already created the patched kernel and custom RAM disk and made them available for download. So if you want to quickly go through the forensic data acquisition, you can skip next 5 minutes of video and directly download the custom RAM disk and patched kernel from the link which I have shared in the article. The forensic toolkit which is released by Sogeti is only available for Mac OS X. So I am going to use OS X on my VMware for this video. In order to run their toolkit, first we have to install few dependencies. Sogeti researchers prepared a very good readme file by listing all the commands to run forensic toolkit. I am going to open the readme file and copy paste those commands on OS X terminal. First we are going to download LDID file. LDID file is used for self-signing. After the download, grant execution permissions to the file using chmod command. After granting execution permissions, move the file to user bin directory. Next, download and install OS X Fuse for image3 file system. Apple firmware files are in image3 format. If you unzip iOS file, you can notice all the components in image3 format. OS X Fuse allows to extend OS X native file handling capabilities via third-party file system. Download OS X Fuse using curl command. It gets downloaded as an image. After the download, use HDIUtil command to mount the image file. Here it gets mounted as volumes fuse OS X directory. Once it gets mounted, we can use installer package and install OS X Fuse. After the installation, eject the mounted directory using HDIUtil eject command. After this, we need to install few Python packages. Mac OS X comes with pre-installed Python, so we can directly install the required Python packages. Here we are downloading PyCrypto package using easy install module. Easy install directly downloads and install the required packages. Here you can notice few warning messages, but you can ignore them. After PyCrypto download, we need to download and install 3 other Python modules like M2 Crypto, Construct and Progress Bar. I am clearing the screen here and downloading the rest of 3 Python modules. Of these 3 Python modules is going to take a couple of minutes. Meanwhile, we can download Mercurial tool which is required to check out the code from the repository. Open a new tab in Safari and browse to mercurial.selenic.com. Download Mac OS X version of Mercurial. After downloading the file, double click on the package to install it. It opens a installer window. Now follow the steps displayed during setup to install it. By this time, all 3 Python modules got downloaded and installed. Next step is to clone the source code, which is available at Google Code repository called iPhone Data Protection. Currently we are in user directory. I am going to check out the source code into the current directory. After running this command, it is going to create a new directory called iPhone Data Protection in the current directory. You can notice that it has downloaded around 120 files. Navigate to iPhone Data Protection folder. It lists out all the downloaded files. Most of them are Python scripts and shell scripts. In order to create custom RAM disk, first we have to supply original RAM disk to the tools. For that, we have to download iOS 5 firmware bundle. You can download this file from getios.com. They maintain all the different versions of iOS for all devices. For this demo, I am going to use iPhone 4 GSM model, which is running on iOS 5. So I am downloading iOS 5 version for iPhone 4 GSM model. Even if your phone is running on iOS 4, you can still download the iOS 5 version because iOS 5 kernel is backward compatible. iOS is a zip file which is around 700 MB in size. I am going to cancel the download because I had a copy already on my machine. I am navigating to folder where I placed my iOS 5 file. Copy this file to iPhone Data Protection folder, which is located in user directory. I am running Mac OS on a VMware, so copying is little slow and it is going to take few minutes. While it gets copying, we can compile image3fsc code, which is in the downloaded toolset. In iOS, different components are encrypted with different keys. This C code is used to encrypt and decrypt iOS components. You can directly run make image3fs command to compile it. If you run into any problems, edit make file and change the GCC compiler path. While making, you may notice few warning messages, but we don't need to bother about those warnings. It is still copying the iOS file. Okay, let's go ahead and download Redsnow tool. Redsnow is very popular tool in jailbreaking community, which is used to build custom iOS and for jailbreaking. It is always good to download the latest version of Redsnow. Current latest version is 9.9 B8. Redsnow gets downloaded as a zip file. So run unzip command to extract the zip file contents. After unzipping, navigate to contents folder inside Redsnow directory and copy the keys.plist file to current directory. Dot inserted at the end of this command instruct it to copy keys.plist to current directory. With this, we have installed all the dependencies to run the forensic toolkit. Now we are going to run kernel patcher Python code by supplying iOS 5 IPSW file to it. This Python code is going to patch the signature checks in kernel. To do that, first it is going to extract kernel from original iOS file. As the kernel is encrypted, required encryption keys are grabbed from keys.plist, which we have already placed in iPhone data protection folder. Later it is going to use image3 fs code, which we have compiled earlier, to decrypt it. Patching kernel is basically binary editing. After that, it creates a shell script to make custom RAM disk. The shell script is going to extract the RAM disk from iOS file. Later it decrypts using image3 fs code. After that, it downloads the forensic toolkit from Google repository and adds it to the RAM disk. The RAM disk image is just a HFS file system which is native to Mac OS, so it is easy to add files to it. Upon successful execution of both steps, we get patched kernel and custom RAM disk. Now we can use jailbreaking tools like Redsnow to load the patched kernel and custom RAM disk by exploiting boot ROM vulnerabilities. I ran into problems while using Redsnow on OS X because I am running OS X on my VMware. So I am going to use Redsnow on my Windows host. For that, I am copying patched kernel and custom RAM disk to a pen drive. Then disconnected the pen drive and connected it to host machine. In Windows, I have created a folder called iPhone Forensics. Now I am going to copy files which are in my pen drive to iPhone Forensics folder. Also download and place Redsnow and original iOS 5 IPSW file in the same iPhone Forensics folder. Connect your iPhone to Windows machine. On bottom of the screen you can notice the device which I am using for forensics, and it is passcode protected. Now open command prompt and navigate to iPhone Forensics folder. Run Redsnow by supplying IPSW file, custom RAM disk and patched kernel. It is going to open Redsnow in GUI mode. Follow the steps displayed in Redsnow to place the device in DFU mode. Once the device is identified in DFU mode, Redsnow is going to use Limra1 exploit to exploit the boot ROM vulnerability. Then it loads the patched bootloader. After that, it is going to load patched kernel and custom RAM disk onto phone. Once Redsnow displayed done message, you can notice some actions on your phone. Initially, it displays a panned boot logo. Later, custom RAM disk gets started in verbose mode. If you see OK message on your device, then it indicates that custom RAM disk is loaded and started successfully. When we booted with custom RAM disk, networking capabilities like Wi-Fi are not enabled. So we are going to use USB MUX protocol to establish a communication between the device and the computer over USB cable. USB MUX is a protocol used by iTunes to talk to an iPhone and coordinate access to the phone services by other applications. USB multiplexing provides TCP-like connectivity over USB port using SSL. TCP relay Python script is going to redirect SSH traffic to a local port. At this point, we can do SSH to the device on a local port. Over SSH, we get access to the file system. But to make things even more complicated, Apple decided to encrypt every file with a unique key tied to a particular OS device. Furthermore, data protection mechanisms introduced with iOS 4 adds another layer of encryption that does not give access to the protected files and keychain items when the device is locked. So we have to supply valid passcode to decrypt the protected files. Passcode validation is performed at two levels, one at Springboard and another one at kernel level. Brute force attack performed at Springboard locks the device, introduces delays and may lead to data wipeout. However, these protection mechanisms are not applicable at kernel level. Demo brute force Python script is going to brute force the device passcode with the help of kernel method called Apple Key Store. Port 1999 opened with TCP relay Python code is used by brute force script. To make brute force attacks less practical, passcode key derived from the user passcode is tied to hardware UID key. So the brute force can only be performed on the device, and it is not possible to prepare pre-compute values like rainbow tables offline. So we can only perform brute force attack on the device. Brute force Python script connects to the custom restored external daemon on the RAM disk, collects basic device information like unique device keys, and download the system key bag and tries to brute force the passcode. 4-digit passcode can be cracked in 20 minutes. You can see that it successfully brute forced the passcode. The passcode is 1234. Brute force script also extract class keys from keybag. These keys are used for encryption when data protection is enabled for files. It also creates a directory with device UDID as the name. UDID is a unique device identifier which is unique for every iDevice. If you navigate to iPhone data protection folder, you can notice a folder with UDID name. My phone UDID starts with B7. Brute force Python script creates a plist file with data volume number and stores the keys extracted from keybag in it. You can open the plist files using a text editor. This plist file is going to be used by rest of the tools. Brute force Python script also downloads keychain DB. Keychain is a SQLite database which stores sensitive data on your device. Keychain DB file can be opened using SQLite 3 client. Keychain database is encrypted. That is the reason you will notice all junk characters when you open with SQLite 3. Keychain also restricts which application can access the stored data. Each application on your device has a unique application identifier, also called entitlements. The keychain service restricts which data an application can access based on this identifier. By default, applications can only access data associated with their own application identifier. There are two ways to access all the keychain items. One way is by writing an application and make it as a member of all the application groups. The other way is by writing an application and granting com.apple.keystore access keychain keys entitlement. Keychain tool Python script decrypts the keychain DB file and displays the output on the screen. You can observe it listed out all the values from keychain including private keys and certificates and passwords of all different applications. If you scroll up the terminal, you can see passwords stored by different applications. Next task is to download the file system. Dump data partitions shell script is going to grab the raw image file system from the device and stores it in the iPhone data production folder under device UDID. Give execution permissions to dump data partitions shell script and execute it. It will take few minutes to dump the file system. Meanwhile, we can start decrypting the files on the fly. In the file system, every file is encrypted with a unique key. So in order to view the files, we have to decrypt the files. We can use EMF decryptor Python code with no write option just to verify that there are no errors in the decryption process. I aborted the process by pressing Ctrl C. Now run EMF decryptor without no write option. Then it starts decrypting the file system permanently. Now you can notice it is decrypting many plist files and SQLite database files, images and songs. The whole process is going to take few minutes. My phone contains around 8 gigabytes of data and it took around 30 minutes to decrypt each and every file. After decryption, we can mount the file system image and look at the decrypted files. I am aborting the process by hitting Ctrl C. We are going to mount the file system, view the decrypted files. In general, iPhone runs with mobile user privileges. So all the information is basically gets stored under mobile folder. You can notice that installed applications and library contacts, SMS and media folder. In media folder you can notice pictures and many more. All these files are already decrypted and you can just view it. Final step in forensics is recovering the deleted files. Before recovering, eject the mounted file system image. Deleting a file on iPhone only deletes the file reference, so it is possible to recover deleted files. With the help of EMF undelete Python script, we can recover some of the deleted files. Later again, you can mount the file system and view the recovered files. This shows that iPhone forensics is still possible on iOS 5. With this technique, it is possible to recover valuable data like call logs, deleted images, deleted SMS, and deleted contacts and deleted